And I am recording. And I'll start out by sharing my browser with you. Okay, and here we are in our course, and you can see in week 11, which is where we are, we did the antiderivative formulas last time. And today we're going to be talking about integration using substitution. I did mention to you in class that integration is a little bit more of an art form than taking a derivative. And as such, you kind of have to look at the function that you're trying to integrate and decide what's the best approach. So there's a little bit more analysis up front when you're doing integration. So we're going to be talking about the substitution method today. And I'm going to be using these notes here, integration using substitution. Okay, so before I get started, let me just ask, does anybody have any general questions about anything we've covered already, or anything about the course, the scheduling, anything like that? Any general questions? All right, well, seeing none, and again, you can always pop those in the chat, or feel free to unmute and just ask. Okay, give me a moment and I'll open the notes for today on substitution. Okay, and let me share these with you. All right, now everybody should be seeing these notes, section 3.4, substitution. Okay, if you can't see them, give me a shout out. Okay, so you might have noticed when we talked about our integration rules last time in class, there really aren't very many of them. We kept using the power rule for integration, which is just the reverse of taking a derivative with the power rule. We used it over and over and over again. And then there was a very basic rule for taking the integral of an exponential, which was the reverse of taking the derivative of it. Same thing for log. Okay, so there aren't a whole lot of rules. That means that when you're doing an integration, sometimes the rules don't apply directly. Sometimes, and I hate to say it, you got to do some algebra first. And I know that's a song I've been singing all semester, right? That you need to do some algebraic manipulation to simplify things before you can do calculus on them. Okay, so you might remember when we did derivatives, one of the things that we dealt with was a composition function. And when we differentiated it, we took the derivative of the outside function, and then we multiplied that by the derivative of the inside function. And we call that the chain rule for taking a derivative. Well, this substitution method gives us a way to, as they say here, unwind the chain rule. Okay, but it requires that when you look at the thing you're trying to integrate, you recognize it as the product of a chain rule. Okay, so how do you recognize it? Well, you're going to see in the integrand, the thing past the integration sign, a function and something that looks like part of its derivative. Okay, so you might see, something in parentheses to a power, and you'll see part of its derivative. Okay, so how do you reverse the chain rule? Okay, well, again, this is just some algebraic manipulation. If you take the derivative of a composition, you get the derivative of the outer function times the derivative of the inner function. So basically, you're just going to integrate that, okay? And you have to be able to recognize these two parts, right? A function of g of x and the derivative of g of x next to it. And here's the trick. The only thing that has to work is the powers on x, or the x parts, okay? The coefficients aren't a problem. We can manipulate the coefficients to be what we want, okay? So the only thing that has to work is the variable part. Okay, so again, let's just take a quick look at this. Okay, this is the recipe from your text. All right, and again, I realize a lot of people get confused with the notation here. Okay, so here's basically the strategy. Let's let u, which is some sort of a function, be part of the integrand. Integrand, that's the part you're trying to integrate after the integral sign. Okay. All right, so a good first choice is look for the messiest piece. Okay. Figure out what the derivative of that is, and then try to match your derivative that you did here of u, okay, to something in the integrand. Okay, and I'll show you the process. It's a lot easier to show you than explain it in words. Okay. Once you do that, you should have an integral that's only in terms of u, and it should be simpler than what you started with. Because what you've done is you've substituted u for a messy bit inside your integrand. Okay, so substitution, like it's an algebraic technique, and it's designed to make things simpler so you can kind of see your way through the forest when you're doing the integration. Okay, at the end, we're going to substitute back the x, the messy bits, for our u, because our original integral was in terms of x. Okay, so I know they said pick u to be the messy bit, but here are some good choices for you. Okay, an expression in parentheses that it's raised to a power. This will also be anything under a radical sign, because we can write a radical as 1/2 power. Can be written with fractional exponents. Okay. So again, I know I'm doing a lot of explaining, and it probably doesn't make a lot of sense till you see it, but it's important to have the steps somewhere. So once you've seen it a couple of times, you can go back and refer to the steps. Okay. Another good choice for you is an expression in a denominator, because you can write that as a quantity in parentheses raised to a negative power. Remember, negative powers give you fractions. They put the quantity that you're talking about in a denominator. Okay. And then any expression, if you've got an exponential function, any expression in the exponent, particularly if the base of your exponential is e. So these are good choices for you. All right. Now, enough talking. Let's actually look at some examples like this so you can see how it works. All right. So here's an example. I have this integral. Okay, it's an indefinite integral or an antiderivative. I have no bounds here, but this method works for definite integrals also. But let's just keep it simple. Okay, I'm looking at this, and none of my general integration rules apply because I'm seeing a quotient. Okay, I have this quantity in my denominator that's not only under a radical sign, but it's in the denominator too. That means I could rewrite this, okay, as having a negative fractional exponent. Okay. Now, according to my rules over here for choosing u, I'm going to let u be the bit that's in the denominator. So let u be 4 minus x squared. Okay, so I'm going to choose u to be the thing in the denominator. It's also under a radical sign. Okay, now, right now, I could substitute u for this thing over here. Okay, but what do I do with the x? Okay, I need to match my x. With part of the derivative. Right, because what I want this to look like is u and at least the x part of its derivative. Well, if you notice in here, right, if I differentiate 4 minus x squared, what do I get? Okay, Well, du over dx, which is like saying, what's the derivative of 4 minus x squared? The 4 gives me a 0, and the negative x squared gives me negative 2x. Okay, so that's just the derivative of this thing. Okay. And unfortunately, I just have x. I don't have the negative 2 part. Okay. I also have dx. Okay, which is not over here. Well, I can fix the dx part by multiplying both sides of this by dx. So now I have du equals negative 2x dx. I'm close now. I have x dx, but I still need to get rid of the negative 2 if I'm going to match this. Well, that's easy. I'm just going to divide both sides by negative 2. Okay, if I divide both sides by negative 2, it goes away on the right. And I have du over negative 2 equals x dx. Why did I do all of that? Well, I did it because I was trying to match the other stuff in the integrand that wasn't under the radical. And now I did that. Okay, so my x dx matches what's in the integral. Okay. The other thing that's important to understand from a point of view of algebra is that du divided by negative 2 is the same as negative 1/2 du equals x dx. Okay? That's not calculus or anything. This is just algebra. Remember, we said in class, dividing by negative 2 is the same as multiplying by its reciprocal. I want to do that because I want to write this as, rather than as a denominator, I want to write it as a coefficient. So now I have all the pieces I need, because now I have u is 4 minus x squared. Okay, and I have negative 1/2 du is x dx. So now I've got pieces for the integrand. Okay, so here's pretty much what I've got. If I translate all those x's, I have negative 1/2 du on the top, and on the bottom I have the square root of u. Okay, which still looks kind of ugly. All right, everybody see how I made the changes? All right, here's the u, and here's the x dx. Okay, is that part clear? That's the bulk of the method. All right, so I'm going to stop here and ask if anybody has questions on what I've done so far. Can you please give me a shout out so I know if you're following along? Is this clear?
It kind of is. I mean,
Okay.
yeah.
Go ahead, ask me a question, Richard, then.
No, I could piece it together. It's just like it's gonna take a lot more practice just to like nail it.
Absolutely, I totally get it. The important thing to understand about the method is you are trying to match bits in this integrand here. Okay, so you pick the messiest bit to be u, and you look for something that looks like part of the derivative of u elsewhere. I can see that the power of the derivative here would be x to the first. So I know this x up here is part of the derivative of this u thing. Okay, once I see that, I know I can use substitution. Okay, so then I differentiate this u thing to get negative 2x, get the dx over there. So now I'm matching x dx. And then I just need to play with the coefficient in order to make sure I'm matching exactly what's in the integrand. Okay, so I just multiplied both sides by dx. You're going to do that every single time to get dx over here. And then you may or may not have to play with the coefficient to get an exact match to what's in the integrand. Here I had to divide by -2 to get an exact match. Okay, that's why I'm highlighting it so you can see what I'm looking at. All right, anybody else, other questions? Okay, this is the critical part of the method. The rest of it is just plug and chug. Okay, but this is the difficult part, is to understand why you're doing what you're doing. Okay. All right. Well, again, feel free to ask as you move along. So then what do I do now? Well, this still doesn't look like what I'm used to. Okay. So let me rewrite it a bit. Okay. The square root of u is in the denominator. Okay. And -1/2 du is in the numerator. So I can rewrite it like this: -1/2. Okay. The u part, I'm going to write it with an exponent. It's an exponent of 1/2 for the square root and a -1/2 because it's in the denominator. And then just conventionally, I can put the du last. All right. So this came up into the numerator with the negative exponent on it. And then everything's multiplied. So -1/2, the du, and the u to the 1/2. Okay. Everybody understand the algebra involved here. Okay. Now that I have this integral, this is a lot simpler than the thing I started with. Okay. All I need to do is pull through my -1/2, which is a coefficient, and all I'm integrating is u to the -1/2 du. Okay. And that's something I can use the power rule for integration on. Okay. So again, the purpose of the method was to take something really messy and turn it into something simpler. Okay, so now I can integrate this new integral in terms of u like this. Okay, I'm going to use the power rule on it. Okay, think about how you do that. It says take your exponent and add 1, and then take the new exponent and put it in the denominator, plus c. Okay, this step 4 here and taking the derivative of u are the only two calculus steps. So step 2 and 4 are the only calculus steps. Everything else is algebra. Okay, algebra and judgment, basically, like picking u. Okay. All right, well, we have to do some cleanup over here, so let's do that. Okay, if I simplify things a little, this gives me -1/2. My exponent on u is -1/2 plus 1, which is u to the +1/2. Okay, so the new exponent's +1/2, just doing this addition, plus c. And then what I can do is I have my -1/2 coefficient. Divide by 1/2 is the same as multiply by its reciprocal. Okay, again, this is just arithmetic. This is not even algebra. Okay, divide by a number is the same as multiply by the reciprocal. You can see these cancel out, and my integral is -u to the 1/2 plus c. So here's my final antiderivative. Okay, now that's not the answer to the problem because the original problem came in terms of x's. Okay, so I need to substitute the x's back. Well, how do I do that? I go back over here and I see what was u. Okay, and basically u was 4 minus x squared. So here's what I've got: -4 minus x squared to the 1/2 plus c. Okay, and that's perfectly fine. But if they don't want it with fractional exponents, or you don't want it with fractional exponents, you're just going to change it to a square root. And that's pretty much the steps. Okay. I'm going to stop again and ask if there are any questions. Are there questions on the process? Okay, any questions? Again, the critical thing when you want to use this method is, first of all, look at it and say, hey, I don't have an integration rule for this. Can I use substitution? Okay, this is my candidate for you because it's the messiest bit. It's in the denominator and under a radical sign. And then you have to say, what's the derivative of this? Well, more importantly, what's the x part? The x part would be negative 2x, okay? And I have the right power of x for that in my numerator, okay? As soon as you see that you have the right kind of x in this for being the derivative of u, you can go ahead with substitution. Okay, that's what it requires that you recognize something that came out of the chain rule. Okay, so function and its derivative. Okay, again, the derivative doesn't have to be an exact match. We didn't exactly match the derivative of u here, but I was able to manipulate the coefficient to work. I couldn't manipulate a power on x to work. So if this had been an x squared up here instead of an x, I'd be stuck. I wouldn't be able to use substitution. I'd have to use a different method, which we haven't learned yet. Okay, so what is critical here is the power on x, okay? Because again, this is a polynomial and its derivative is 1 power less, okay? Had this been a cubed, I would have looked for a squared up here. Does everybody see what I'm trying to point out? I'm trying to tell you how to recognize it. Okay, how to recognize. Yeah, I'm trying to tell you how to recognize when to use substitution. Okay, because that's the important part. Okay. Well, let's just keep going through examples so you can see how this works. All right, so here's my next example way down here. And it's got exponentials in it. Okay. So again, here I've got some messy bits. Okay, I'm seeing a quantity in a denominator with a power on it, okay, which they told me was the messy bit, and I should pick this to be u. Okay, so let me highlight that. This is my u. Okay, and you have to be familiar enough with derivatives to realize the derivative of this inside, e to the x plus 15, is just e to the x, right? Because the derivative of e to the x is e to the x, the derivative of 15 is a 0. Okay, so you're looking at it saying, oh, okay, well, all I need to match up here then is this e to the x business, dx. Okay, so if I let this quantity down here be u, I've already got its derivative up here. Okay, that's what you have to see to make sure that you can use substitution. Okay, and this won't be the only method we're using for integration. So it's important to realize, you know, that this is what unwound from a chain rule. Okay, so I'm going to let u be, oops, sorry, let u be e to the x plus 15. Okay, and here, if I take its derivative, the derivative of u with respect to x, that's just e to the x. And the only thing I need besides the e to the x is the dx. So all I'm going to do is multiply both sides of this by dx. The dx's cancel over here, and I get du equals e to the x dx, which now matches the rest of my integral over here. See the numerator part. Okay, so now I get to actually do the substitute part. which is to take the integral and substitute the bits, okay? The x dx was up in the numerator, so that's just du, okay? And then down here, I had u to the third, okay? That still looks a little strange to me, so why don't I rewrite that as u to the minus third. That brings it up in the numerator with du. Okay, now it looks like something I'm familiar with integrating. Okay, again, you can see here, not only do you need to remember what are the derivatives of basic functions, you have to be really, really familiar with rules of exponents here. Okay, because you're doing this constant algebraic manipulation. Okay, and if you need to, okay, I put the rules of exponents in the course, have them handy so you can keep referring to them until you're comfortable enough with them. You don't need to look them up every time. That's how you get familiar, is practicing. Okay. All right, so this looks a lot more of a simple integral than what I started with down here. Okay, e to the x dx over e to the x plus 15 to the third. Okay, so I'm going to use the power rule to integrate it. Okay, so here's the calculus bit. I'm going to take my exponent and add 1 and put that over the new exponent plus c. Okay, so the power rule part is super simple. Okay. And again, if you want to think about it, let's just do the addition up here. This is going to be u to the -2 over -2 plus c. Again, I'm just showing you it this way to show you that I'm using the power rule. If you're comfortable enough adding 1 in your head and getting u to the -2 over -2, do it. Okay, I'm not showing you every blessed step to say you have to do it that way. I'm doing that to make sure I don't lose anyone. Okay, if you can do it faster and stay accurate, do it faster. Okay, the last step is put back all the x's for u. Okay, so I have u to the -2, and u was e to the x plus 15. So that's to the -2 over 2 plus c. That's certainly correct, okay? But it's not conventional, okay? This -2 would put this expression in the denominator with an exponent of 2. What would be left in the numerator? Well, a 1. Okay, and by the way, this is a -2. Okay, so I'd have -1/2, and then I'd have e to the x plus 15 squared plus c. Okay, and remember, you can stop at any point. I mean, I'm pretty sure Moore would accept this as the answer, okay? But you ought to be comfortable enough with algebra that you can take this, divide by -2, put it out front as -1/2, and then flip this down into the denominator with a positive exponent. Okay? Everybody all right with that one? Anybody questions on example 2? I'll try to get all the steps on the screen at the same time. Anybody questions on any of these steps? No? Okay. Made sense the whole way through. I'm so glad. The terror of my life is when I stop making sense. So please let me know if that happens. Okay. All right. Let's look at one that has a quantity in an exponent. Okay, so the two examples we looked at before had something in parentheses raised to a power, whether that was a square root or in a denominator, it didn't matter. Okay, here's one that has a function up here in the exponent. Okay, suppose, according to our rules, we let u be x squared. Isn't 2x the derivative of x squared? So this is the derivative of that. So substitution ought to work. Okay, so I'm going to let u equal x squared. And then I'm going to do the same business, take du over dx. That's 2x. Okay, so here's what I got so far. Here's my u up here. Okay, what's the other bit that I need to match? I need to match 2x dx. Okay, well, take a look. I got the 2x for free when I took the derivative of x squared. All I need to do is multiply both sides of du dx by dx. The dx's cancel on the left, and I get du equals 2x dx, which is exactly what I wanted. Okay, everybody see the match to the integrand? Okay, do you see the match to the integrand? Okay, this is the critical piece. This is what you need to be able to see. Okay, the rest of it is just push and algebra. All right. All right, next step is doing a translate. So I'm going to have, what am I going to have? I'm going to have e to the u, and the yellow part here is just going to be du. So I have the integral of, integral of e to the u du. Well, that's easy because e to the whatever is its own integral, is its own derivative. So this integrates as e to the u plus c. Okay, so that's like the world's easiest integral. And then all I need to do is substitute back in the x's. So instead of u, I have to remember, oh, what was u? U was x squared. So let me put that back in. Okay, and here's a sanity check. If you were to differentiate e to the x squared, what would you get? Well, the way you differentiate an exponential is that's to e, it's just the same thing. So you'd get e to the x squared, but because you have a function up here, this is a composition. It's a quadratic inside of an exponential. So you take the derivative of the e part, which is e to the x squared, and you'd multiply it by the derivative of the exponent, which is 2x. Well, what do you know? That's what we started with. 2x e to the x squared dx. Okay, so that's always a check that you did the integration correctly, is you can differentiate it back as a check. Okay, and see that you get what you started with. Okay. Anybody question on this one? Questions on example 3? Questions on example 3? Okay. All right. I'm going to add a page in here right now because I think you guys need to try this. And I'll make one up. Okay, we'll do an indefinite integral. How about this? Try to make one up. Okay, here's one for you to try. Okay, and here are the steps. Choose U. Determine. Okay, determine what du is. Okay, I guess the way they said it in the book was this way. I'm going to write it like this. Match the rest of the integrand. Okay, by that I mean the part that isn't u. Okay, substitute. Use 4x's. 4 is integrate. And the last step is substitute x's back. Okay, so you give this one a try. Okay, and then you can type done when you finish. Okay, so type done when you finish. Okay, also message me privately if you get stuck. Okay, there's a feature in the chat. You can say instead of 2, you can pull down the menu bar and just pick one person. So pick me and let me know you're stuck, and I'll work with you privately. Okay, but give this a shot. take another minute or two on this one. I know there's lots of steps. You can go back and look at our previous examples if you get stuck. Or ask. Okay, folks, I know you're all still working because hardly anybody said they were done. I'm not quite sure if it's just taking you a long time or if you're stuck. So here's what I would propose. Let's all come back together and work through the steps together, and then I'm hoping you'll give me a little bit of feedback, okay? So let's work on this one together. Okay, so what should I choose for you in this problem? What should I choose for you? Anybody suggestions? Okay, Richard says choose the thing in parentheses raised to a power. So I'm going to say let u be x cubed plus 1. I think that's a good choice, right? It's the most complicated thing in the integral. Then I need to take the derivative of that. That's what du dx means. Well, du dx, if I look at x cubed plus 1, I'm going to differentiate x cubed with the power rule, 3x squared, and the 1 gives me a 0. Okay, so that's the derivative of this. Now, if I look at my integral, I can see, well, I got the x squared up here. That matches. And I know I can get the dx to the other side by just multiplying both sides by dx like this. All right, these go away, and I get du equals 3x squared dx. What should I do with the 3? What should I do with the 3? This 3. It doesn't match anything in the integral. I just want x squared dx. Anybody have any suggestions? Yeah, divide 3 out from both sides. So this is going to give me du divided by 3 equals 3x squared dx divided by 3. Okay, and that's going to leave me with du over 3 equals x squared dx. Okay, and now that's a match. If you take a look at the integral, this x squared dx matches the stuff in yellow. The only suggestion I have is rather than writing du over 3, I'd write 1/3 du equals x squared dx. And again, I'm only doing that, okay, to make sure it's a coefficient that I can pull through the integral. Okay, when it's down here, I kind of don't know what to do with it. But divide by 3 is the same as multiply by 1/3, and 1/3 I know I can pull through the integral. Okay, so now I'm going to substitute in my integral. Okay, the x dx is up on top, so that's 1/3 du. Okay, and my u is down here to the 5th. Okay, everybody see the substitution? There's the u. Again, let's color code so you can see what I'm doing. Okay, those are the bits that are being substituted. All right, so far so good. Now this doesn't look like anything I'm comfortable integrating, so I'm going to use some algebra to rewrite it. I see u is in the denominator with an exponent of 5. I can bring that up to the numerator as long as the exponent's -5. Okay, so now I have the integral of 1/3 times u to the -5 times du. Everything's all multiplied. Yes? Okay, so algebra got me that far. Okay, now I'm actually going to do the integration. The first thing I'm going to do is pull through the 1/3. I can do that up here. All right, and now I can use the power rule for integration on what's left. All right, so that's 1/3. Okay, u to the 5th, -5th, plus 1 over -5 plus 1 plus c. There's the calculus bit. Okay. Everybody comfortable with the power rule for integrating? It's just the reverse of differentiating. The rest is just do some arithmetic cleanup. Okay, -5 plus 1 is -4. Okay. Now, these two fractions are multiplied, yeah? So I have 1/3 times a -4 in the denominator. I could write that as -1/12 u to the -4 plus c. Again, I lost my plus c here. Okay, everybody comfortable with what happened here? This is just multiplying fractions. 1/3 times 1 u to the -4th over -4. Multiply the numerators, multiply the denominators. And I'm pulling it all out in front as a coefficient. Okay, but everybody sees the -12 down here, right? Okay. Last step is substitute my x's back. Well, I said u was x cubed plus 1. Okay, so there's the substitute my u thing back with the x's. right? And if you want to write it without negative exponents, that expression needs to be down in the denominator with a 12. So there are the steps. Okay, now here's what I need back from you. Please, everybody who's on the call, please participate. Okay, you see how these steps are numbered? 1, 2, 3, 4, 5. Okay, what I need you to do is to type in the chat the number of the step where you got stuck. Type in the chat the number of the step where you got stuck. That will help me help you. Okay, so everybody should type a number from 1 to 5. Okay. Come on, there's about 11 people on the call. I need you guys to participate, please. Where did you get stuck?
It's starting to make more sense, kind of.
Okay, good. But seriously, it matters as to whether you got stuck taking the derivative up here, doing the substitution, doing the integration. If you got most of the way through, that's great, but can the rest of you please let me know where you're getting stuck? Just asking for a number. What step you got stuck on?
Number 2 for me was the was where I got more lost, but I figured it out this time.
Okay, taking the derivative. Okay. That is kind of tricky because you're not used to the differential notation. Okay, but really the step is algebraic. You're just trying to get the stuff on the right side to match what's up here left over once you pick U. Okay, anybody else have a step where they were particularly stuck? Right. Well, I do appreciate the two of you who gave me feedback. Thank you. Again, the integrate step is going to be new to you for a while. Okay, and again, I think what's confusing about step 2 is the differential notation. If you treat it more like a matching exercise, I think that'll make it clearer. You're just trying to get the right-hand side of your equation to look like what's left over in the integrand. Okay, and as you can see, there's a lot of algebra that you have to do in order to proceed. Okay, so if you're rusty on the algebra and you don't want to say so here in class, you can always reach out to me and I can give you things that'll help you practice or work with you, whatever you want to do. Okay, don't stay confused. Okay, it's not likely to get better on its own. Ask for help. Okay, that's the only thing I'd ask. Okay, so I have a question in the chat. Okay. All right, over here, one of the questions is, how did you get this 1/3 over here when it was in the numerator? Okay, what I'm trying to substitute for is x squared dx, which I got to be 1/3 du. You can see that over here. Okay, 1/3 du equals x dx. All right, so I put the 1/3 du up in the numerator where the x dx was. Okay, but if I've got a fraction in the numerator, okay, think of it this way, its denominator is actually downstairs. Okay, again, part of it is being comfortable with fractional numbers. And I know a lot of students are not comfortable with fractional numbers. Okay, as far as being able to do something like this and say, all right, this 1/3 du, I could write it down here as 1/3 du without a denominator once I get this guy out and put him up here. Okay, so in all honesty, what I did here is I got rid of u to the 5th in the denominator, and now it's upstairs with the 1/3 du. Okay. Okay, so again, any other questions? It's important that you get your questions answered. Okay. Not seeing any? Let's talk about how this generalizes to a definite integral. Okay, so let's look at definite integrals. Okay, so that starts down here. Okay, so when you do the substitution on a definite integral, remember those have bounds on them. They have limits on the integration. And there's two ways you can handle it. In reality, what you're doing when you do u substitution is you're changing your variable of integration from x to u. So one method is to actually create u limits of integration. Basically, substitute the existing limits into your equation for u and put new limits on the integral. That's this b part. If you do that, you can skip the translate back to x because you'll already have what you need. All you're going to get out of this, remember, you're not going to get a function in terms of x like we did with all the antiderivatives. You're going to get a number. So as long as you change the bounds on the integration to u bounds as opposed to x bounds, you'll get the same number. It'll be okay. And you'll be able to skip a step of substituting x back. Now, that said, lots of people find that confusing. So the other alternative, step A, is you can solve the antiderivative as a side problem, translate everything back to x's like we did, and then use your original limits of integration. Okay, so advantage, part A, the A method is just like what we did for antidifferentiation. There's no difference. There's just the additional step of evaluating your antiderivative at the upper bound minus lower bound. Okay, so this is just like antidifferentiation. Sorry, trying to erase things. Okay, this one is shorter. Okay, but different. Okay, now I know from my past students, a lot of students just want one way to do it. They don't want to have to remember, well, if it's like this, do it like that. If it's like that, do it the other way. It's confusing. So this is your choice. I will warn you, the homework for this section is going to ask you to do it both ways, okay? Especially the substitute the limits, okay? So I'll show you both ways. Okay, so here's the substitute limits idea in general. Your original integrand is in terms of x. It has x limits on it. You're going to substitute those values that are the limits into your function for u and get u limits because your new integrand will be in terms of u. Okay, and again, you don't need to do the substitute back, because all we're going to get out of a definite integral is a number. Okay, so let me see if I can find where we're going. I stapled all my stuff upside down, so give me a minute. All right, let's look at an example. Okay, so both methods have drawbacks. A usually involves some messy algebra, but it's just like the antiderivative case. So there's no new strategy to remember. Method B is difficult to understand conceptually, that you're changing your integral bounds from x bounds to u bounds, but it's shorter. It's not as messy because you don't have to do the substitute back. Okay, we'll show you both. And again, if you're doing this in more may tell you which to use. If you're just doing calculus on your own, the choice is whichever method you prefer. Okay, so let's take a look at this one here. Okay, now you might look at this and say, wait a minute. Okay, how would I use substitution? Okay. And I'm telling you, this problem is one you can do with substitution. Okay. Basically, I'm going to let u be this quantity in parentheses. And if you think about it, what would be the derivative of that quantity in parentheses? Well, the derivative would just be a 3 with no power of x. So that would work here. Okay. Because again, I can take care of the constant that doesn't match. I just can't take care of a power of x. All right, so this derivative has x to the 0 as the power of x in its derivative, the derivative of this. And that's what I've got here. I don't have any other x's that are visible. Okay, so I'm going to do it with the antiderivative as a side problem, method A first. Okay, so I have my 4 steps. All right, so I have step 1, let u be 3x minus 1. Okay, step 2 is take its derivative, du dx equals 3. Now that doesn't match anything, okay, that I have here. The only thing I need to match is my 1 dx, okay? So you could think of this as 1 times dx, okay? So first let me get dx over there. I'm going to multiply both sides by dx. Cancel that out. So I have du equals 3 dx. I need to get rid of the 3. So I'm going to divide du by 3 and 3x dx by 3. Not 3x, 3 dx by 3. Okay, so I get du over 3 equals dx. Okay, so now that's a match. Okay, the only difference is I'm going to write that as 1/3 du equals dx. Right, so this is the algebra manipulation piece. Now, if you take a look, okay, everybody understand the steps here, okay? The derivative of u is a 3. What I have to match is just the dx. So I multiply both sides by dx to get that over here on the right side, which is where I'm trying to match. Okay, the dx's cancel. All right, and then the last step is divide out the 3 because there's no 3 outside of my parentheses here. So I divide both sides by 3, and I get du over 3 equals dx. And I'm just going to write that du over 3 as 1/3 du, so I have a coefficient to pull through. Okay? And all I'm trying to do is to match what's outside this set of parentheses, which is just the dx. Okay, the next step is to substitute that into the integral. Okay, so my integral now becomes, I'm going to do the antiderivative first, so I'll skip the bounds right now. Okay, this is going to be u to the 4th times 1/3 du. Okay, here's what I substituted for dx, and there's what I substituted for 3x minus 1. Okay, I might just pull that 1/3 through. 1/3 comes through, and I have u to the 4th du. Okay? That's the substitution step. Now I have the integrate step. Actually do the integration. I'm going to use the power rule. Okay? So that is basically take my exponent, add 1, and put it over the new exponent. Okay, I'm not going to use plus c because I'm going to need to evaluate it at limits. Okay, and I don't need the plus c when I've got a definite integral. Okay, so this is 1/3 times u to the 5th over 5 Okay, you can think of the plus c is there, but I'm not going to need it because I'm doing a definite integral. All right, so I'll put it there so you know I'm not just forgetting it. Okay. And then I need to substitute back. Okay, so this is 1/3 3x minus 1 to the 5th over 5. Okay. Now I need to evaluate it at my original bounds, 0 to 1. Okay, now here's the trick with definite integrals. Pull out as many coefficients as you can. All right, so this can be rewritten as 1/3 times 1/5 3x minus 1 to the 5th, evaluated from 0 to 1. Okay, what I did was I took this 5 in the denominator, divide by 5, and wrote it as 1/5. All right, so that gives me 1/15 out here, 3x minus 1 to the 5th, 0 to 1. Right? The only part I need to evaluate is the part with the x's. So here's what I'm going to do. Evaluated x bounds. I'm going to pull out the 1/15 because it's going to apply to both the upper and lower bound. Okay. And then I have 3 times 1 minus 1 to the 5th. That's my upper bound. Okay, put in the 1 there for x, minus 3 times 0 minus 1 to the 5th. That's my lower bound. Okay, so everybody see the bounds over here? I got 1 here going in, and I have 0 over here. Okay, so I'm plugging those in. Evaluate at the bounds. Okay, this is 3 minus 1, so that's 2 to the 5th. Okay, which is 32, minus 3 times 0 is 0, negative 1. Negative 1 to the 5th is negative 1. Okay, so this is 32 minus a negative 1. Okay, which is 33. Okay, over 15. 33 over 15. And that's approximately 2.2. Okay. So again, you can certainly do all of this on a calculator. Just type it in the way it looks, like this. I'll just show you so it's obvious. Okay, so here it is on a TI-84. Okay, so here's my 1/15. And again, you can do this on any scientific calculator. You just might need to parenthesize more. Okay, so instead of square brackets, I'm going to use double parentheses. 3 times 1 minus 1 to the 5th. Step out of the exponent. Here's the lower bound, parentheses. 3 times 0 minus 1 to the 5th. And close the parentheses that would be square brackets. Okay, so here's exactly the way you would type it in. Okay, here's my upper bound expression. And this one's my lower bound expression. You can see I got 11/5, which is the same as 33/15. Okay, I just divide out by 3. And if I want it as a decimal, 2.2. Okay. Everybody okay with part A? Okay, so this is the method of leaving the x bounds alone and just doing the antiderivative as a side problem. Okay, and then you plug your x values back in and evaluate at the x bounds. Okay. Anybody questions on these? Okay. I'm going to wait a minute to see if there are any questions. Okay. Okay. Nobody has them. All right. Thank you, Richard. All right, let's try the other method. We're substituting the limits of integration, means we're going to use u limits, okay, instead of x. The first two steps of the problem are exactly the same. Let u be 3x minus 1. Okay, I have to figure out what du dx is. So I'm going to do that exactly the same way. All right, that gives me a 3. I just want dx. I don't want 3. So I'm going to multiply both sides by dx. This is exactly the same as what we did before. Okay, so I have du equals 3 dx. I don't need the 3, so I'm going to divide that out. Okay, and I'm going to get 1/3. Du divided by 3 is 1/3 du equals dx. So that's the same exact steps. I have my u value and I have my dx value. Okay, the next step is where I need to make a change. Okay, calculate new limits. Okay, so my lower limit on my integral used to be 0. So I'm going to take my expression for u and I'm going to plug in a 0 to it. 3 times 0 minus 1. Okay, so 3 times 0 is 0, minus 1 is -1. My new lower limit, my u limit, is -1. My upper limit means I plug in a +1. Okay, so again, 3 times 1 is 3, minus 1 is 2. Okay, so now I have my new integral, step 3, that looks like this. And it has bounds on it because I'm not going to substitute the x back again. My lower bound's -1. My upper bound is now 2. I just calculated those. Okay, and the integral is u to the 4th times 1/3 du. Again, using the same things I substituted in. Okay, that goes in for dx, and that goes in for 3x minus 1. Okay, everybody see it? Okay, now 4 is do the integration. I'm going to pull through the 1/3. Okay, and this is going to give me the same thing I got before, u to the 5th over 5. The only difference now is I'm evaluating that from -1 to 2. Okay, and I'm not substituting x back. Okay, so this is the last step. Okay, I can pull out the 1/15 like I did before. Okay, and now all I have is 2 to the 5th minus -1 to the 5th. Okay, so these are the bounds on the integral. Here's the upper bound. Here's the lower bound. Okay, and just so you can check, we get the same thing. 2 to the 5th is 32. Negative 1 to the 5th is negative 1. So 32 minus a negative 1 is 32 plus 1. So 33 over 15. Which again is approximately 2.2. So you can see we got exactly the same value. Okay. So let me ask you, which method do you prefer? A or B? Which method do you prefer, A or B? Okay, Richard likes B. Anybody else have a preference? I think B is faster. Okay, as long as you remember to recalculate the limits on the integral. Gil likes B, good. Okay, excellent. Okay, as long as you're comfortable with recalculating the new limits, you're good. Okay. All righty. Let's take a look. Okay. I have at most like 2 more problems. Okay. So I'm going to do one more where I show you both methods of doing a definite integral. And then I have one for you to try where you can do it whatever way you like. Okay. So here's example 5. Okay. I have a log integral. Okay. And you might remember that the derivative of ln of x is 1 over x. So you could conceive of this integral like this. Okay. Again, you can write this as a product of ln x to the 6th times 1 over x times dx. Again, remember, divide by x is the same as multiply by 1 over x. This is the algebraic and numeric thinking you've got to be able to do to simplify this stuff. All right. And 1 over x is the derivative of ln. So I'm thinking I can do this with substitution. Okay. So I'm going to do it the first way where I handle the antiderivative as a side problem. So I'm just going to treat it like it's not a definite integral. Okay, so step 1 is let u equal ln x, and I'm picking that because it's in parentheses and it's raised to a power. Then I'm going to find du dx. So here's what I've got so far. I'm matching that to that. Okay, I've got my u. Okay, and du dx is 1 over x. Okay, I actually need 1 over x dx. That's easy. I'm just going to multiply both sides by dx. And I get du equals 1 over x dx, which again is what I'm trying to match over here. Okay, so now I have all the bits. Okay, now I get to substitute into the integral. Okay, so I have, I'm not going to put bounds on it. I'm just going to make it an indefinite integral because I have to substitute x back before the bounds make sense again. And this is going to be u to the 6th. Okay, so there's ln of x is now u. Okay, and 1 over x dx is du. Okay, so that turned out to be a pretty simple integral. Okay, integrating it using the power rule. I'm going to add 1 to the exponent, put that over the new exponent. Okay, and I'm not going to write the plus this time. I'm just showing it to you. All right, so just added 1 to the exponent divided by that new exponent. Now I get to substitute my x's back. Okay, so what did I say u was? I said u was ln of x. So that's ln of x over 7. Okay. And now using my original x bounds I had from 2 to 10. Okay, so evaluated x bounds. Okay, I'm going to pull through the 1/7 in the denominator. Get comfortable doing this step because it makes life easy, and you'll typically have stuff in the denominator after you use the power rule. Divide by 7 is the same as multiply by 1/7. Okay, and then when I evaluate the definite integral, I can just pull the 1/7 out in front. Okay, it doesn't need to be in each term where I do upper minus lower. Okay, I can just pull it out in front. Okay, so this is going to give me ln 10 to the 7th minus ln 2 to the 7th. Again, if you want to see where I'm substituting from, here's the upper bound. Okay, and here's the lower bound. Okay, and these are my original x bounds. This is something you would want to do on a calculator to get a number. Okay, so you'd have 1/7 and then parentheses, ln 10 in parentheses. So I have ln 10, and I want to raise that to the 7th minus parentheses ln 2 raised to the 7th. Okay, step out of the exponent, close your parens. Right, and you get a value of about 49.01. Okay, again, remember this is area under a curve between 2 and 10. Okay, so that's doing it with antiderivative on the side. It's got extra steps because I had to substitute my x back in so I could use the x bounds. Now, if I want to use the u bounds, here's what I'm going to do. I'm going to have the same first two steps. Okay, and I'm not going to go through doing the du dx. I'll just say du dx equals 1 over x, and that means du equals 1 over x dx. Okay, so I'm shortening it so we can get everything done in time. Okay, here's the new step where I have my new limits. Okay, so my lower limit was 10. Okay, but that needs to go into u equals ln, and I'm substituting 10 for the x. Okay, actually I have it backwards. That's 2. 2 is my lower limit. My upper limit is 10. So that's u equals ln 10. Okay, now when you're actually going to do your integration, okay, your integration is going to be with bounds. Okay, ln 2 is your lower bound, ln 10 is your upper bound. Okay, these are your new u bounds on the integral. Okay, the substitution part works the same way. Okay, you're going to have u to the 6th du. And again, those got substituted from the things you came up with for u and for du. Okay, and if you integrate it, you're going to get Okay, so here's the integration step. I'm kind of running out of vertical space, so I'll do my best to fit it without jamming it. Okay, so integrating it with the power rule is going to give me u to the 7th over 7. And now I'm not substituting x back in. This goes from ln2 to ln10. Okay, and I just put those values in there. I'm going to pull out the 1/7. So it's a coefficient. And then this just becomes 1/7. ln10, there's the upper bound to the 7th, minus ln2 to the 7th, that's the lower bound. You can see right here that this is the same exact expression, okay? It's just that my bounds are now the whole thing, okay? So ln10 is here, ln2 is there, but this is the same exact expression as I got up here. So I don't even have to evaluate it. I know it's going to be 49.01. Okay, so this is fewer steps as long as you correctly evaluate your new bounds. All righty. So let me ask if you've got questions on example 5. Anybody questions on example 5? Okay, I'm showing you both ways. Okay, and I'm showing you you get the same value either way. It doesn't matter. All righty, not seeing any. Okay, so why don't you try example 6? Use whichever method you prefer for handling the bounds. All right, so you try example 6. Type done when you finish, or message me if you get stuck. Okay, so type done when you finish, or message me in the chat privately if you're stuck. I'll scaffold some steps for you. Okay, I'll get you started. Okay, we'll take like another half a minute to get this one going because we're getting close to the end of our class. Okay, folks, in the interests of ending on time, I know you're all working. Most of you are all working. So let's just come together and see if we can walk through the steps. As long as you got started with this, it's okay. You'll get better at it as you practice it. So please give the homework a try and ask me if you get stuck or you have questions. So in this problem, I'm seeing something underneath a radical sign that has 1 minus x squared in it. Remember, I can think of a radical sign as a set of parentheses with the exponent 1/2 on it. And I'm seeing something out here that looks like part of the derivative of this thing under the radical sign. Okay, the power on the derivative of this would be 1. Okay, because this is squared. When you differentiate something squared, you get x to the first. So I'm thinking substitution would work here. Okay, I know this is a lesson on substitution, so you're making the assumption all the problems are solvable with substitution. When you meet integral problems or integration problems in the wild, there's nothing to tell you that other than the pattern of function and part of its derivative outside. Okay, that's how you're going to recognize it. So I'm picking 1 minus x squared is u. When I differentiate that with respect to x, I get negative 2x. The negative sign comes from this minus in front of x squared. I need to match x dx. So the first thing I'm going to do is get the dx over there. Always do that step. Multiply by dx on both sides. The dx's cancel out on the left, and you're left with, let me not combine steps. Okay, you're left with du equals minus 2x dx. Well, you're close, except you don't need the negative 2 there. So you're going to divide both sides by negative 2 to get rid of it. And that's going to give you du over negative 2 equals x dx. Now you have a match on the right-hand side of this to the yellow stuff that's left over in the integral. The only other step I'm going to do is I'm going to write divide by negative 2 as negative 1/2 du equals x dx. Okay, and now I have a match to the other piece of my integral. Okay, so this part's going to be u under the radical sign. This part, x dx, I'm going to substitute with 1/2, negative 1/2 du. Okay, now I want to do this with u bounds because it's faster. So I'm going to compute new u bounds. All right, so my lower u bound is going to be u equals 1 minus, my lower bound was 0 before. Okay, so I have 1 minus 0 squared. I'm just substituting it into my expression for u, which gives me a new lower bound of 1. Okay, and then I have my upper bound, okay, which is u is a 1. Okay, so that's 1 minus 1 squared, which is 0. Yes, I know they're backwards. Don't worry about it. It'll all work out. Okay, so here are the bounds. My u bounds, Okay, and then I'm substituting my bits in. I have the square root of u, and the x dx I have as negative 1/2 du. Okay, so there's the integral, right? I'm going to do a little massaging of it algebraically first to make it easier. Okay, the first thing I'm going to do is I'm going to pull through the negative 1/2, and I'm going to write my u as u to the 1/2 du. Okay, so what I did here is I pulled the constant, the coefficient through, and I rewrote u, square root of u as u to the 1/2, so I can now use the power rule for integration. Okay, so doing the integration, so here's the substitute, here's the integrate. Okay, so that's going to be negative 1/2, that's out there no matter what. Okay, and I'm adding 1 to 1/2, so that's going to give me u to the 3/2 over 3/2. Okay, convince yourself that 1/2 plus a whole, another 1 is 3/2. Okay, and this is going to be evaluated from 1 to 0. I'm going to do a little bit more numerical manipulation first, right? Divide by 3/2 is the same as multiply by 2/3. Okay, so now up front, if you look at this fraction, I have negative 1/2 times 2/3. The 2's cancel out, and I'm left with negative 1/3 u to the 3/2 from 1 to 0. Okay, so now I just have to put the bounds in the right order, right? So evaluate at bounds. And again, it's upper minus lower. Okay, don't switch them around because you think they should be in a different order. Okay, it's always upper bound minus lower. So again, my negative 1/3 comes out front because it applies to both the upper and lower bounds. And now I have 0 to the 3/2 minus 1 to the 3/2. Okay, so upper minus lower. And just to convince you I'm not making stuff up, I'll do this on my calculator. I can just get the chat over here so I can see it. All right, so here's the evaluation. So I have negative 1/3 out front. Okay, and then I have parentheses. My upper bound is 0. And I'm going to raise that to the 3/2 power minus 1. And I'm going to raise that to the 3/2 power. Okay. If some of you are cutting to the chase numerically because you're saying, wait, 0 to any power is 0 and 1 to any power is 1. So this is all negative 1. You're right. Okay. All right. So this is going to be negative 1 times negative 1/3, which should be positive 1/3. Okay, so the area under this curve is positive 1/3. And if you did it using the antiderivative as a side problem method, you should have also gotten 1/3. Okay. So questions on example 6. Anybody have questions on number 6? No? All right. Okay, I'm glad it's making sense. As you practice it, you'll get it. And the important thing is be sure that you ask questions, even if you've got algebra questions while you're doing it. The worst thing you can do at this point is just throw down the pencil saying, I don't get it. I'm lost. Don't be willing to be confused. Ask for help. I'm more than willing to help you. So if folks don't have any questions, do you have any overall questions?